I think I can teach more. Parallel, perpendicular. Can't talk about that, Dad. Because we're doing this. What?
Why after you start school, you was picking on and she walked out?
She's gone.
Good.
I guess. She said she was going to withdraw, but I haven't gotten the form yet. So I don't know. She's not coming. So. Of course, you didn't come last week, and she didn't come
Hey,
last
hold on, it
week.
was raining. I walk here.
So you come in wet.
What? Are you crazy? Getting my notes messed up?
Backtracking. 2-1. I'm going to try to teach this as slow as possible.
That's kind of hard for you.
Yes, it is. So I'm going to try to be wordy about it. Functions. Let's graph one first.
Please go slow.
I am. I'm graphing. Graph y equals x squared minus 6x plus 7. I think it'll work. We'll find out. So if you don't know how to graph something, the only way to do it is to table it. But this gets to the essence of what a function is and how I want you to work with them. So over here you put x. X is also known as the domain, or independent variable is another fancy name for it. On the other side, we'll go y, and this is called the range, or the dependent variable, where x is independent, y is dependent. And we're just going to punch a bunch of x's into this equation and see what kind of y coordinates we get out of it. And this is pretty much how functions work. If I tell you what x is equal to, you should always tell me what y is equal to. This is just one of the little basic things that everybody forgets, which is funny. And I'll pick on you as we go through it, and I'll say, well, here's x equals 2, and I'm expecting you to tell me what y is without me asking what is y. So what value should I start with? Most people say 0. How boring. Is 0 the first number you've ever made up?
-2.
Negatives would be good to start at. But I'll tell you right away, negatives aren't going to work really well on this one. I'll do one of them, -2. So up here, this is what I would highly suggest you write. Parentheses squared minus 6 parentheses plus 7. It's the representation of what y is equal to in symbolic form. So you're going to take -2 and plug it in. Put -2 here. It becomes, now that's why I like these parentheses, because then you take the -2 and mentally put it in the parentheses. -2 squared
4.
is 4. -6 times -2 is positive 12 plus 7. And the answer becomes 23. On a piece of graph paper, we can kind of locate it. It's -2 to the left and 23 up. Most graph paper doesn't go 23 up unless you get the whole sheet one. So where I'm going to start this is, where you told me to start anyways, 0. But technically you should try some negatives, 0, and some positives. Alright, plug in 0. 0 squared? -6 times 0? And then you just pop out a 7. What did I just find? Specifically called? What is it?
Y.
Y-intercept. Whenever you let x equals 0, you're finding the y-intercept. So this coordinate 0, 7 is the y-intercept. Alright, numerically just go in order, plug in 1. Integer. Don't do fractions, that gets messy. But you can put in fractions and anything else you want. Plug in 1. 1 squared, 1. Negative 6 times 1, negative 6. Plus 7. What is it? 2. Plug in 2. 2 squared, 4. Negative 6 times 2, negative 12. Plus 7. Negative 1. 3. 3 squared, 9. Negative 6 times 3, negative 18. Plus 7. Negative 2, right?
Yeah.
That would be negative 9 plus 7. 4. 4 squared, 16. Negative 6 times 4, negative 24. Plus 7. That's negative 8 plus 7 is negative 1. 5. Oh, notice what's different also. If this was a nice line, I wouldn't need all these points. Obviously, this is not a line. There's no pattern going on. The jumps are all over the place. So we have to kind of keep going until I see a pattern. 5 squared?
25.
25. 5 times negative 6. And then plus 7. Positive 2. There's a positive 2 up there. Maybe a pattern. Let's see. 6.
30.
Oh, maybe I should have done negative 1. No. Hold on. I messed up, don't worry. 6. 36. Minus 36. Plus. So we get back to 7. And if you look at this, it goes 7 to negative 1, negative 2, negative 1 to 7. They kind of go down and then they come back up. So that's the pattern I'm looking for. So if we graph it, we get something that looks like this. It's mostly on this side. 1, 2, 3, 4, 5, 7. And then how many down? Negative 2 is all I have to go. Negative 2. Plot points.
What about that 23?
Negative 2, 23. If you want me to, I can plot it on the wall, but it's not worth it. So start off with the first point that we can plot, 0, 7, which is right here. Get rid of this marker too. So 0, 7. Next point is 1, 2. So x is 1, y is 2. Next point,
2, negative 1.
2 to the right, down 1. Next one, 3, down 2. 4, negative 1. 5, positive 2. 6, back up here, 7. Now, if I just leave the points like this, I get a nice plot. What do most people do? Connect the dots. This is a polynomial, and I'll tell you one thing about polynomials, they're smooth, rolling, continuous curves. So they always have a nice smoothness to them, and they don't have sharp turns in them. So you can't have a V anywhere. So when you draw this, you're assuming that all these other points coincide just like this, or something really, really close to this. And you get what's called a parabola. And this is a function, and there's a reason why it is a function. For every x I chose, there's exactly one y. It doesn't generate two different y's. And there are certain graphs that generate, for every x, two y's. I can think of one somewhat quickly. This, for every x, there are two y's. This equation. Why? Well, if I let y equal 2, what's 2 squared? 4. If I let y equal -2, what's -2 all squared? 4. They give you the same x, so 4 has 2 y values associated with it. This would not be a function. So what I want to do is define a function precisely. And the way we're going to deal with functions is this empty set of parentheses idea all the way through the whole book. And they make things a lot easier if you do it that way first. So what is a function formally, definition-wise? So definition. Function, well, let's start off with relation. Y squared equals x is a relation. It's a weird looking graph. A relation is any set of ordered pairs. Ordered pairs is just coordinates on a piece of graph paper, x, y. A relation is any set of ordered pairs. A circle, a zigzag, a weird spiral graph, that would be a relation. The kind of way my brain thinks about it is you take a piece of graph paper, you put it on a dartboard, and you take a bunch of darts and you just chuck it at the dartboard. Assuming you can throw darts decently and it hits the graph paper, anything that it hit is a relation. Any point in any pattern, it really doesn't matter. So this is still a relation. It is a set of ordered pairs, 0, 7, 1, 2, 2, -1, and so forth and so on. So this graph that we did over here it's a relation, but that's not the best that we can do with it. The best we can call it is a function. So a function is a relation. In other words, it is a set of ordered pairs. But there's a specific way we have to pick them, where every domain value, better known as the x's, has only one range value, better known as the y's. Functions, in a sense, ask a single question, and they want a single answer. How tall are you? I'm 5 foot and 6 foot. Most people don't say that, right? When you ask the question, you get one answer. This is the type of things I want. So when we ask a question, we're asking a question of x, and x is going to answer one answer, which will be considered y. Now what's funny is most people don't understand this definition, even though it's very, very concrete and precise. So let me give you some examples. Relation A has -3, 2, -1, 7, 0, 3, 1, 8, and 3, 7. Okay. Set B, relation B, it's going to be -3, 2, -1, 5, 0, -3, -1, 7, and 3, 8. One of them is, well, actually, both of them are relations. Guaranteed without a doubt, they're both relations. But one is a function and the other one is not. Which one is a function? A, you think? I'm paying devil's advocate, don't mind me. B, you think? Think of the definition. For every x value, there's only one y value. So as you go through here, -3 has 2, -1 has 7, 0 has 3, 1 has 8, 3 has 7. Does every x value have one y value? The answer is yes. So the top one must be a function. Go to the bottom one. -3 has 2, -1 has 5, 0 has -3, -1 has 7, and 3 has 8. Why isn't that a function? What's that? That -1. -1 is 5 feet tall, but he's also 7 feet tall. That makes absolutely no sense. So B is not a function, and A is perfectly fine as a function. It doesn't matter that the y values are the same here. When I talk to this class, if I asked everybody's height in here, trust me, 2 people would be about the same height, right? I mean, it's not impossible to have 2 people that are 6 foot tall. But it is impossible for one person to be 2 different heights. So that's what's going on here between A and B. So a definition that most people understand, a function does not repeat x values. In other words, you're not going to have 2 values of x in a function, like -1, -1. That's 2 separate x values with 2 separate y values. That doesn't make any sense. So that's another definition that we can throw at you. All right. There's a graphical way of doing this. Give you 2 graphs. One is a function, the other one is not. And they look very similar. They got the same shape. So the shape has nothing to do with it. So which one's a function and which one's not? Go by definition. Pick an x value. Here's x. How many y values are associated with it? 2. There's 1 above it, and there's 1 below it. So pick an x over here. Another 1. Is there anything above it? No, there's just a point below it. So which one better fits the definition of what it means to be a function?
Y1.
The second one. For every x, there is only 1 y. So this is a function. And this one is not. So this one actually leads into a test. It's called the vertical line test. If I draw a vertical line and it hits the graph more than once, then the graph is not of a function. If I draw any vertical line here, how many times is it going to hit the graph? Just once. So this one is a function. So that would be called the vertical line test. Function only if all v lines hit only once. Any more and it's not a function. So if I ever ask on a test, is this a function? You have to say, yes, it's a function because every vertical line only hits it once. You can't just say, it's a function and be done with it. You have to tell me why, because, function, not function, it's like flipping a coin. It's like true, false. Anytime I ever have a true, false on a test, you have to explain everything. Why you chose the answer you did. All right. Huh? Oh, B? Yeah. Well, actually, on Math 140, I'll do true, false. It is the most missed question ever. I could ask the simplest thing in the world, and they'll be like, oh, and they'll guess, and then guess wrong, generally. Okay, so we did definition of function, vertical line test. What else is there? Of course, function notation. I always do function notation a little strange, or at least describing it. Yeah, don't be talking about my Frank and George yet. What's the y-intercept? And before you answer, you're going to have to ask me a question. What's the y-intercept? One answer. What's the y-intercept? Which one? The problem is, eventually we're going to be talking about 2 functions at one time. And by the way, both of those are functions. They're lines that are not vertical slopes, so they definitely are functions. All lines are functions except for vertical, because they pass on the vertical line test perfectly fine. So when we start talking about 2 or more functions, there has to be a better way of saying it other than the one on the top, the one on the bottom, the one whose slope is 3, the one whose slope is 4. There's got to be a better way of describing it. So one of the better ways of doing it, I like doing, it's called one of them Frank and the other one George. Because if I say, what's the slope of Frank? Most people would say, I hope, 3. What's the slope of George? 4. It's the number next to the x, by the way. So now, just by labeling them Frank and George, you know which one to look at. Well, mathematicians are lazy and they don't like writing out Frank. So they replace Frank with F, just F. So when you see F in an equation, it is not a variable. It is a literal name, and my name for F is Frank. And it's read the function F. The function called F. All right. Then if you see G in an equation, by the way, these will never ever be variables. G is read the function called G, or George, Gabriel, Gertrude. That was my grandmother's name, Gertrude. I used to pick on her. Hey, Gert. 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 Ah, she's cursing me from heaven now. Oh well. The other thing that's nice about function notation, calling things Frank and George, is this. If I have y equals 3x plus 5, and I want to find y when x is equal to negative 3. Remember what I said about mathematicians? They're lazy, and that just took up all my breath to write down. So there's got to be a better way of writing it. Well, let's do it the old way first. Let's do it the old way. How do I find y when x is equal to negative 3?
Y equals 3, parentheses.
Huh?
Y equals 3.
Oh, y. I thought you were telling me y equals 3. I'm like,
No, I didn't say that.
y equals 3 times
Parentheses, negative 3.
negative 3 plus 5. I was looking for replace the x with negative 2, but that's okay. So this becomes negative 4. Woohoo, great. One problem with this method is my information is separated. I have one piece of the information down here and the other piece of the information way over there. I like them to keep them close together, so I can write it as a coordinate. What's the coordinate?
Negative 3, negative 4.
X is equal to negative 3, y is equal to negative 4. So that would be the point I'm talking about when x is equal to negative 3. So two things are bad with this. Number one, it took too long to write it. Number two, after I got my answers, I had to collect the information rather than having it come down together. So to fix that problem, make things a little bit nicer, well, for me, maybe not you, we're going to change y equals 3x minus 5. We're going to let Frank, who operates on the variable x, replace our y. So in this form, we're saying the name of the function, f, we're telling what variable it works with, x, and we're going to replace y with this expression, f of x. So this is read f of x, f of x, f of x. So after I replace it, I get f of x is now equal to 3x minus 5. So Frank works with x, and what he does with x is he multiplies it by 3 and he takes away 5. That's all it does. It's kind of directions of what it's going to do, the cookbook. All right, doing the same thing, asking what is y equal to when I let x equal negative 3, I don't even have to write all those words. Now all I have to write is this. Because just writing that, I've already said that x is equal to negative 3, and f of negative 3 is going to replace y. So when I say f of negative 3, the whole thing, this whole thing represents y. So it tells me both of them at the same time. It tells me what x is equal to, and it tells me how to get to y. And then the process is exactly the same. Whatever goes in this set of parentheses goes in this set of parentheses. So if I plug in negative 3 here, what do I plug in here? Negative 3. Did we write the right answer over there? Oh, wait a minute. Plus.
Yes,
Oh, see, I put plus 5 down here, but I should have put minus, I wanted to talk about the same one, but let me change this back to plus. Plus, plus, plus. So we get f evaluated at -3 is equal to -4. And the cool thing about this notation is, here's the x value, -3. Here's the y value, -4. That's the coordinate, -3, -4. Ta-da! So it simplifies the question, and it organizes the answer, all in one fell swoop, just by changing y into f of x. Reasonable? Get used to it, because it gets worse. And the better you use these parentheses, the easier this stuff gets. So for instance, if I say that g of x is equal to x squared minus 5x plus 1. And I'm going to ask you, well, what the heck is g of 2 equal to? The first thing you do is not even worry about the 2. The 2 is irrelevant. The 2 could be anything, any number that you want. What's important is the form of the other side. You're going to take a number, and you're going to square it. You're going to take -5 and multiply it by that number, and then finally you're going to add 1. The form is much more interesting. I call this skeleton form. It has just the bones of the problem. The 2 happens to be the meat, and then you put it in there. Meat, why not? You know, meat, bones, I'm hungry, so. So you take the 2 and you plug it in to the parentheses. Anywhere there's an empty set of parentheses gets that 2. And then you do your calculation. 2 squared, 4, -5 times 2, -10. 4 minus 10 is? -6 plus 1.
-5.
So g evaluated at 2 is -5, also known as the coordinate to -5. Ta-da! Isn't this easy?
For now.
For now. What if I want something a little weirder? What if I want g of a plus 2? So here I'm saying let x equal a plus 2, find me what y is equal to. The steps are exactly the same. It's going to be some number squared minus 5 times some number plus 1. Just leave empty parentheses and then worry about what you're going to plug into those. What goes into those parentheses? Well, whatever is over here. I don't care what's over here. The same thing gets stamped into both of these. So this is g of a plus 2. So a plus 2 goes here and here. A plus 2 all squared. Minus 5a minus 10 plus 1. Did I do that right? Yeah. Distribute the negative. And then combine like terms. G of a plus 2 is equal to
A squared minus 5.
minus 5. Don't forget the plus 1. Now, when I plugged in 2 and I got to the end, I wrote the coordinate 2 comma -5. So what's the coordinate of this one? Well, what's the x coordinate? What's x equal to? A plus 2. What's y equal to? Notice the pattern here. The 2 just comes down, the -5 just comes down. So it's a plus 2 comes down, and the a squared minus a minus 5 is the y coordinate. It's kind of messy, right? So there's a better way of writing it. A plus 2 is still the x coordinate, but I could write, instead of a squared minus a minus 5, I could just write the other side. Well, the other side is just g of a plus 2. So that's another way of writing a coordinate with function notation. Isn't that neat? Bet you don't like that. Nobody likes that. But it comes in very handy to be able to talk about a point that you know nothing about the graph. I don't know what g is, so I can at least represent y as ga plus 2. g of a plus 2.
So we don't need to do all that work.
Well, no, I'm going to make you do all that work. What I'm talking about is, this is one I forgot all about. I really shouldn't have, because I usually like teaching it. Which equations are functions? How do you determine if an equation is actually a function? When can you put that f of x notation in there? So first off, what makes a function a function? Let's see if you remember. For every x, there's only one y. Very specific, it has only one value. It's like asking a question and getting one answer back. You want multiple answers. So if I give you an equation that looks like x squared plus y squared is equal to 9, is this an equation a function? How would you determine it? Well, you'd have to find out if you put it in x, are you only going to get one y? And probably the best way to do that, and this is a general direction, solve for y. Where else do we just solve for y as a direction that's kind of hidden in the question? Y equals mx plus b? When you want to find the slope and the intercept, one of the hidden directions is solve for y. Basically, write it as a function. All right, so if I want to solve this for y, what do I do first? Move the x squared to the other side. So you get y squared is equal to 9 minus x squared. That's easy. Then what? It's already being squared. Square root of it. I didn't hear the root part. There's a big difference between square and square root. So you square root both sides and you get y equals? Oh, plus or minus. Remember, if you square root both sides of an equation, you tag in that plus or minus. Then it becomes the square root of 9 minus x squared. Can you simplify the square root of 9 minus x squared? Notice my tone. The answer is no. But better yet, hell no. The only thing you can do with square roots to simplify them is if there's a product or a quotient. You cannot mess around with pluses and minuses. Do not take the square root of 9 and make it 3, and the square root of x squared and make it x, and make this x minus 3. This is the square root of 9 minus x squared. All right, now let's determine if it's a function. Let x equal something. Easiest number to let it equal? 0. If you plug in 0, you're going to get y is equal to plus or minus 3. What does that mean? Well, it means when x is equal to 0, y is equal to 3 as one of its coordinates. But it also means that when x is equal to 0, y is equal to negative 3. Is that a function? No. For every x, there should only be one y, and this one actually has 2. By the way, the graph of this thing is a circle. Can a circle be a function? Fails the vertical line test. Remember that? We talked about it. If a vertical line hits the graph more than once, it's definitely not a function. So this one is not a function. Without a doubt. All right. What about this one? X cubed plus y cubed is equal to 27. X cubed plus y cubed is equal to 27. Is it a function? How would you find out? What's the hidden direction? Solve for y. When in doubt, solve for y. So this becomes y cubed is equal to 27 minus x cubed. It's kind of the same steps involved. Then stare at it, okay. And then, how do you get rid of a square? You would cube root this one because you're trying to get rid of a cube. So you cube root both sides, you're going to get y is equal to the cube root of 27 minus x cubed. Again, you can't break it down. You can't say the cube root of 27 is 3 and the cube root of x cubed is x. It doesn't work that way. Do I need a plus or minus?
No,
Why?
because it's a cube root, it's not square root.
Right, square roots you have to worry about principal roots, and cube roots you only have to worry about itself. Because, I guess basically, the cube root of negative 8 is equal to negative 2. Oh, cube root. Cube root of negative 8 is equal to negative 2. So the sign is irrelevant for cubes. Even indexes you have to be really careful. So, if I plug in x is equal to 0, just a random point. Danger of doing this, if you choose one where it only has one point, it doesn't guarantee it's a function. Because someplace else it might have two separate y values like this one. Like if I chose x is equal to 3, I'd come up with one y value, 0. But that doesn't mean it's a function. So I try to find a value that shows that it's actually 2 y's for 1x. This one though, you're going to get y is equal to 3. It's exactly one coordinate, 0, 3. Now, do a little analysis. Why is this one not a function without looking below my arm? What made this thing turn into 2 y values? Because of the plus or minus. So here's a little hint. You run into a plus or minus with y on one side and a plus or minus on the other side, not a function. Can't be. Because you're going to get 2 y values for every x. What's missing over here that this one had? It doesn't have the plus or minus, so this one is a function. So when you solve for the y, if you get a plus or minus, it's not a function. If you don't get a plus or minus, it is a function. Right? There's one other possibility. It's kind of rare, but you never know. X plus the absolute value of y is equal to 5. Function or not? What do you think? Why not? And it's good to go on the y, isn't it? See, if it was absolute value on the x, I could care less. I could care less if it was on the x. What I care about is what's happening to the y. So when you solve this thing, you're going to get x plus y is equal to 5, and x minus y is equal to 5. So when you solve it, you're going to pick one x, you're going to get 2 different y's, not a function. So you have to be very careful what's happening to the y variable. You really could care less what's happening to the x variable. 2, 1, and 2, 2, reading a graph. You're all like, oh, I know how to do this. Yeah. So let's start off with something simple. Small graph. Doesn't have to be very interesting. Let's make it linear. A line. Now, the one thing I like talking about with just a line is what to do with those arrows. What do those arrows really mean? And you have to be really careful. When you're talking about rectangular coordinate systems, there's no such thing as moving along a slant. There's no way of doing that in a rectangular coordinate system because all there is left, right, and up, down. So when you get to these arrows, you have to interpret them correctly. They're actually doing 2 things at once. One of the things it's doing is going up. That arrow on that side is going up. But it's also moving to the right. So if we're talking about horizontally, where is that arrow going? Well, it's going to negative infinity. Right? And if I'm talking about vertically with this arrow, it's going to up infinity. Positive infinity. Positive infinity. And when we get to this arrow over here, it also has 2 motions. One of them is going to the right, and the other one is going down. So if we're talking about horizontal motion, then this arrow is actually pointing to... Come on, Matt, you can stop that. Where is it going? Positive infinity, or just plain old infinity. And this arrow pointing down, if we were moving vertically, this means it would be moving negative infinity. So that's how you would interpret the arrows. Now, one of the things we're going to be talking about is domain. What is the domain of this graph? Now, when you talk about domain, you're only talking about the x-axis. So that means you can only pick values from the x-axis. You cannot look up and down. So basically what you're going to be saying to yourself is let me do this in blue. As you're moving along the x-axis, and you always move in this direction, you always move left to right, as you move along, is there a graph above every one of these x values? Or below it? And your answer should be, is there a graph above it? Is there a graph below it? Yeah. So these values would all be in the domain of this function. But this function goes off to negative infinity along the x-axis and positive infinity along the x-axis. So we say the domain is from negative infinity to positive infinity. It goes all the way to the left, and it goes all the way to the right. Another way of writing that is all reals. That double bar R means real numbers. Real numbers. Easy, right? Yeah? God. It's like talking to a wall. Huh? All right, let's go to the other possibility, range. The range of this graph. Then we're only looking at y values. This is the only one that you look up and down, literally reading the y-axis. Everything else comes from the x-axis. Domain, range, increasing and decreasing. Most of them come from the x-axis. The only one that comes from the y is the range. So when you look at this graph, you're going down, right? And you only count the values of y. Now here you're saying, is there a graph to the left or the right? And the answer is, for all those marks, heck yeah. There's some on the left, and there's some on the right. All right, so that means, how far down do these marks go? Negative infinity. How far up do they go? Positive infinity. So this one is also negative infinity to positive infinity, or all reals. Okay. Then you get to the idea of increasing and decreasing. So let's put in increasing. When is this graph going uphill? Now you have to remember, you're not traveling right to left, because that would mean you're going uphill. Graphs always travel left to right. They always travel towards the positive x-axis. So as this graph is traveling towards the positive x-axis, where's it going? Is it going up? If this was your stock prices, what would you be doing? Selling them, because it keeps going down forever and ever. So is it ever increasing? Nope. So what you put is null set. That means there are no values in the y-axis where this graph is actually going uphill. All right, when is it decreasing? What would be the good English word for that? All the time. It's decreasing for the entire trip. Its slope is always... What kind of slope does this line have? Say it louder, please. What do you want? Whispers here. It's a top secret. It's negative. Oh. So this one is always decreasing, so negative infinity to positive infinity. The same as the domain. Same as the domain. Whew. Think I'll put this one on the test? Heck no. Way too easy. All right. So when do they get worse? Let's keep it somewhat simple. How about this graph? And let's say this is the lowest point at negative 1, 3. Lowest point at negative 1, 3. That has a special name. It's called the minimum. It's the minimum value for this function. It's actually called the absolute minimum because there are no other points smaller than that one. But we'll come back to that in a second. All right, so what is the domain of this function?
This infinity, right?
Which one?
Infinity.
Just a positive infinity? Now remember, domain is x-axis, so you have to look at the x-axis and ask, is there a function above it and or below it? So as you're moving along the x-axis, is there a graph above or below that mark?
No.
There isn't?
Oh.
There's one.
Yeah.
There it is. And how far out can I go with this? Well,
Only keep going.
that one, but that's negative infinity.
Oh.
Right. So it starts at negative infinity. Remember, this arrow up here represents it's going that direction. That would be negative infinity. Then you hit the green graph, and you have the green graph until you get to about here. Does it keep going along the x-axis? Will I always find a graph above it? The answer is yeah, because this arrow represents it's always moving to the right. It's not going vertical, because you can't have a vertical line on a function. It always has to keep on moving. So the domain is negative infinity to positive infinity. All right. How about range? 3 to infinity? Yeah. Because if you come down here, is there a graph to the left or the right of that y value? The answer is no. So when do you start getting the graph? Well, when you get to this point, which is the lowest point is. Don't pick the -1 because that's an x value. Ranges are always the y value. So this thing starts at 3, and both of these arrows are going up. And it doesn't matter if both of them are going or only one of them is going, the graph is going to positive infinity. So the domain is all real numbers, but the range gets cut a little bit. There's no graph below 3 on the y-axis, so we don't count that. All right, what about increasing? When is this graph going up as we move left to right? Well, on this part of the graph here, what are you doing? You're decreasing until you get to that point. Once you hit that point and you come this side, what are you doing? Increasing. So this side we're increasing. This side we are decreasing. Some graphs are like that. Not all of them, but some graphs are. So when is it increasing? What interval? Now, do I look at x values or do I look at y values? Only the x. So it starts increasing when? At -1. And it stops increasing when? Infinity. All right, what about decreasing? When is it decreasing? Or on the decrease? Negative infinity, because it's all the way to the left. So you say negative infinity, all the way up to 3 is a y value. Or talk about x. The only one that talks about y values is right here. Don't ever look at any y values other than him. So it would be -1. Now, depending on your textbook, I think this one put brackets on -1, but technically, at -1, it's neither decreasing nor is it increasing. You're pretty much at a standstill. You're just there. So some books will put parentheses on the -1, but if you put parentheses or brackets, I'm not going to worry about it there. Range and domain, you definitely need to make sure you have the right kind of brackets or the right kind of parentheses on these numbers. So I get very particular about that. So far, so good? All right, let's make it worse. Those are the coordinates of the closed circle and the open circle. This is a piecewise function. There's different domains for different functions here. Now, when I ask the domain of this, there's only one domain for this function. This graph is one function, not two. So I'm not looking for an answer for the left and then an answer for the right. I'm looking for the answer of the graph, the entire graph of f of x. So, first question. This will be a little strange. Which one? Yeah, so what is it, 3 or -3? So f evaluated at 2 is -3. You go to 2 on the x-axis and you find the graph. And the graph is right below it on this point, -3. Probably a trickier question would be to ask this. I don't know what the precise points are, but I can kind of give you a glimpse into how to find them. If I have f of x is equal to 4, what is that telling me? This one is telling me right away that x is equal to 2. What is that one telling me? F of x is equal to 4. It's what? It's y's value. So this here is telling me that y is equal to 4. So on the graph, what you do is you draw the line y equals 4. What does the graph of y equals 4 look like? Is it vertical? Horizontal? Horizontal, right? So this would be, if this is 2, this would be about 4. So let's say 4 is here. You draw the horizontal line y equals 4. How many times does it hit the graph? Twice. One's over here, and one's over here. So this question, if I said f of x is equal to 4, find x, how many answers would you be expecting? 2 of them. So the best way to do that type of problem is to actually draw that line in there, see how many times it hits the graph, and your values are going to be right below it. So this one over here is probably like -4, and this one is probably like 5. So the answer to this would be x equals -4 and 5. Now, how many answers can f of 2 have? Can it have 2 answers? Why? I have a heart attack soon. Why can f of 2 not have 2 y values? Because then it wouldn't be a function, and this f tells me it is a function. So f of 2 is going to have one answer. F of x equals a number could have multiple answers, or none. Could have actually none. How about this one then? I'm running out of room here. F of -2, what's it equal to? What's open circle mean? Included or not included? Not included. This one is actually equal to nothing. That empty circle there has a height of 1, but it's not part of my graph. That's what open circles mean. It's not there. I can just represent it. So f of -2, even though the coordinate of it is 1, it's not on the graph, so I can't even include it. It's not part of the domain. It's not part of the domain. All right. So let's find the domain of this then. What is the domain of this graph? Now be really careful. We're moving left to right here. All the way from the left, all the way to the right. So how far left does this function go? Negative infinity, because this arrow up here is pointing in that direction. So negative infinity. How far does it go? Does it go when it has all x values from negative infinity to positive infinity? To what? To -2. See, the graph comes down and it comes to a complete stop. There's nothing between here and there. It's a gap. So I have to stop it at -2. Now, bracket or parentheses? Parentheses because of the open circle. Union.
What way?
The graph starts up again. Where does it start up on the x-axis? At 2, right here. Right there at 2. So we're going to put a bracket because it's a closed circle. 2, where's it going to? Positive infinity, because this arrow is constantly moving to the right. So the domain of this function is all real numbers from negative infinity to -2, but not included, and then starts again at +2 and goes off to infinity. But there are no values between -2 and +2. It's completely empty void space. All right, what about range? Now remember, this is the up and down motion. How far down does it go? Is it way down here? Nothing here, nothing here, nothing here, nothing here. When does it start? -3, this point. So the graph is going to start on the y-axis at -3. It's a solid point, so I'm going to put bracket on it. How high does it go? Well, is there a graph to the left or the right as I move up my y-axis? And the answer is there any gaps? No. And if I draw a bunch of horizontal lines, it's always on a graph all the way up to the top. So this thing's going to infinity. Even though there was a gap on the domain, there is no gap on the range, which is kind of interesting. All right, those are the three easiest pictures I can come up with. You ready for the hard ones?
You're not gonna do range on the other set of points?
Oh, increasing, decreasing. Yeah, thanks. Increasing.
No, like for range, you just do one set of points, you don't do both set of points?
What do you mean both set of points?
Well, you got negative 2, 1, and you got 2,
Oh.
3.
Range doesn't matter if it's on the left or the right.
Yeah,
One
but
or
when you do like 1,
well,
two.
basically what you're saying is here's -3, right? So is y equals -3 part of the domain or range? Yes, because there's a point there. Is y equals -1? Yes, because there's a point there. 0? Yes, because there's a point there. Now you get up here to 4. Yes, it's part of the domain because there's a point to the right, but there's also one to the left. It gets accounted for. As long as it's one or the other. See, range is a little funny because you could have more than one.
So you don't have to do both sets.
It's 1, 4 that is in the graph. You don't care if it happens twice or 3 times. It's in the range. I can explain that a little bit easier with points, so I'll come back to that one. All right, when is this graph increasing? Starts at 2. Remember, don't look at the y values. You don't care about where it is. All you care is that it's going uphill as you move left or right. So it starts at 2, ends at infinity. Because it's always increasing, always going to the right. So it increases from 2 to infinity. Uphill all the time. Decreasing.
Negative
Negative infinity to -2. Now, if you take the increasing and the decreasing and you put them together, what do you get? The whole domain. So most functions, if you take the increasing and decreasing and put them together, you get the entire domain of the function. There's a couple that are funny that actually have constant, but there's so many functions that are not constant, it's almost not even worth talking about. And they get a little weird too, so. The book might have some constant where it's a flat line. Just call it constant interval. All right, let's make the graph ugly. As much as possible. I'm gonna make it a little bit bigger. Somewhat straight up and down. This is the type I like putting on my test. Hint, hint. Well, I drew it badly, but that's okay. We'll go with this one. All right, ready? No. F of 2 equals. -1. This tells you on the inside that x is equal to 2, so you go to the graph where x is equal to 2 and find the graph either above it or below it. To get to it, you have to go down 1 unit. So this becomes -1. How about f of, try to graph that right, -3. Where do there you go. Well, this tells you what to tell you. That x is equal to -3. So you go to x equals -3 on the x-axis, which is over here, and you find the graph either above it or below it. In this case, it's up. How far up? 5 units, right? It's all the way to here, which is 5 units high. So this would be 5. F of -3 is equal to 5. Okay. If I say f of x is equal to -3, what does that tell me? That's my y value. So this is a fancy way of saying y is equal to -3. Remember, f of x and y are the same thing. There's just different notations for it. So you go to y equals -3, which is down here. And you draw a horizontal line. How many times does it hit the graph? Everybody says once. I love that. Hits it twice. I didn't draw my horizontal line long enough, did I? This arrow's going where? Down forever. So if I drew my horizontal line, even though it misses the arrow, there's still a point over here someplace. So this one actually has 2 answers. So you got to be really careful. I could make the arrow really short, way up here, and you'd be drawing your horizontal line way down here. You have to interpret that the arrow is eventually going to run into that horizontal line. So one of the answers I can tell exactly, you go to this point and you find the x value associated with it. X is equal to 4. Now the other one I'm going to have to make up because I didn't plot it properly. Let's see, if that's 5, that would be 6. 6 maybe? -6? Give or take a little bit? You know, if we extend it out and say that it hits the line there. Yeah, let's just say -6 for kicks. So that's how you would answer those answers. If you know what x is equal, you look up and down. If you know what y equals, you have to look left and right. Same thing with domain and range, by the way. Okay, how about the domain of this function? I usually write capital D, but I'm trying to be somewhat precise. How far to the left does it go? And when does it go to the right? Because remember, domain is just left.
So there's gonna be 2 different order paths?
Well, that's a start. It's going to be 2 different intervals, not ordered pairs. Ordered pairs are coordinates. But I know what you meant. So how far to the left does it go? It stops at -6?
It's
Coming down.
Ah, what did I tell you about these arrows? How do you read them? It's an arrow going to the right, and it's also going down. It's not going totally vertical because it has to be a function. So how far to the left does it go? -infinity. How far to the right does it come? You know, as you travel your graph, what x values are you hitting? Well, you're stopping at, supposed to be -1. I misplotted it now that I look at it from this side. It's supposed to be at -1, so let's move it over. It's supposed to be here. There. All right, so it stops at -1. Union. There's 2 pieces because it's a piecewise function and it's separated its domain. When's it start up again? 2. Where does it go to? Infinity because it's going up? Or infinity because it's going to the right?
Both.
What are we talking about here?
Oh.
Domain only moves left and right. So this arrow, what we're looking at is it's moving to the right. So it's 2, 2, infinity. Once you do enough of these, it starts becoming natural. You look at just the axis. You're not looking at the graph. You're just seeing what values of the axis has a graph. So don't be following the graph because that'll get you confused. Because you'll be thinking y as you move up, and really you're moving left to right. So you have to be a little cautious with that. Range, which I usually just represent with an R. How low does this graph go?
No lower than -3, right? Oh no, it's infinity.
It's infinity. Why is it infinity? Because this arrow over here is going down. How far down? Well, down forever. So it's negative infinity because of that one arrow. Then as you move up the graph, is there any gaps in a y value? No. Because as you move from here to here, there's actually a couple graphs left and right. Here, there's about 3 pieces going across. When you hit this gap here on these 2 points, is there any gap in the domain? Well, if I pick this y value, is there a graph to the left or the right? Well, yeah, way over here and way over here, but that doesn't matter. There is one. So the domain doesn't miss anything as it moves from top to bottom. And just because this one planes out and stops here doesn't mean this side isn't continuing off to infinity. So you have to kind of broaden your view when you hit range. Range gets tricky. Domain should be easy because all you're doing is looking left and right. But for some reason, when people look up and down, they kind of miss either that arrow or that arrow. So be really cautious. Negative infinity, positive infinity. All real numbers. It hits them all on the y-axis. All right, increasing. When is this graph going uphill? Well, as we move left to right along this graph, what are we doing? Over here. Is this increasing or decreasing? Don't be looking at this arrow. We're moving left to right. So as you move left to right, what are we doing? We're increasing. Our stock prices are going up. That's a good thing. So this is increasing. Let me get that in here. So increasing is what interval? Remember, x values, not y. How far to the left? Negative infinity. That arrow is pointing in that direction. So it goes from negative infinity all the way up to? Don't be looking at the y value. Look at the x value. Negative infinity all the way to here, which is negative 3. Union. Where else is it going uphill?
4.
From 4 over here. On this part of the graph, it's going uphill forever. Not because of the arrow, but because as you move left to right, you're always going further and further up the y-axis. So it starts at 4 and ends at, well, it never ends. It's always growing after that point. All right, so what's that leave for decreasing? Decreasing. Well, the rest of the domain, so from where to where? Negative 3 to? Negative 3 to negative 1. So this interval here, it's decreasing. Negative 3 to negative 1. Where else is it decreasing? 2 to 4. It's going downhill in that little portion too. So this would be 2 to 4. So that would be domain, range, increasing, and decreasing. The last thing I want to talk about is these 2 values. I drew the graph a little bit poorly over here. This should be the top of the hill. Top of the hill. I didn't draw it as well as I wanted to, but that should have been the pinnacle of that graph. It has a special name. It is called the maximum. But is it the biggest value that y ever gets on this graph? And the answer is no, because this side is going off to infinity. So what we call this is a local max. It's kind of like saying, I'm the richest person in Tarboro. But does that mean anything if you move to New York City? No, because Donald Trump is there. So this is just the largest point in his neighborhood. And his neighborhood can be any size, but you try to keep it kind of small. So it's a little bump. He's in Tarboro. He's the richest person in the world in Tarboro. But over here, someone else is richer. All right. This point down here is at the bottom of the heap. So we call him a local minimum. So he's the poorest person in Tarboro, but is he the poorest person in the world? No, because over here there are a lot more poor people going down. It gets to negative infinity. So these are called local mins and local maxes. Now if you had a graph that looked like this, the pinnacle is a maximum, but it becomes known as an absolute maximum. In other words, he's the richest person in the world. Everybody else is poor. So this would be an absolute max. Absolute vodka max. Oh, guys are boring. I just said absolute vodka and I got one. That was funny. You're humorous. All right, so if I ask for what the heck is the local max, this is what I want you to answer. If you ever get to calculus, there's another way of answering it. You just tell me the coordinate. That one is -3, 5. Local max. -3, 5. And the local min is, what is that? Local min. 4, 3. In calculus, it gets a little fancier. It says the local maximum happens when x is equal to -3 and has a value of 5. The local minimum happens at x equals 4 and has a value of -3. So it gets a little fancier, but if you just tell me what the coordinates are, I'm kind of happy. Whew. Domain, range, increasing, decreasing, evaluating points, and all that fun stuff. Break time. And I still have to talk about your question, and I'll get back to it. I know what I want to do with yours.